Yeah, I can see it. Yes, great. Yeah, so the
Okay,
next talk,
very good.
yeah, is by Senthil from MIT on non-commutative field theories for some composite Fermi liquids. Yeah, Senthil. I'll give you a warning 10 minutes before the end of your talk. There.
All right, wonderful. Thank you. So thanks to the organizers for putting this together, and thanks to all of you for coming to this talk. So this work was done with Jiwon Dong, who's a graduate student at MIT, and we just posted a paper today. It appeared in today's archive. So, you know, this ultra-quantum matter, in this entire business of thinking about ultra-quantum matter, the gift that keeps giving is the quantum Hall effect. So presumably everybody has seen this trace, the longitudinal and Hall resistivities in a 2D electron gas as a function of magnetic field. You know, all kinds of wonderful things happen in the quantum Hall regime. And, you know, essentially an infinite number of examples of ultra-quantum matter. Perhaps the most striking experimental realizations to date of ultra-quantum matter. So as I think everybody knows, when the filling fraction is an integer, you get the integer quantum Hall effect. And when rational fractions like 1/3 or 1/5, you get the fractional quantum Hall effect. Now, my interest in this talk is in fillings like these, like 1/2, where it seems like nothing is going on. So the system is metallic, rho xx is metallic, rho xy is not quantized or anything. And we see that rho xx is much smaller than rho xy. So this metallic state, it turns out, is actually very interesting, and it's what's known as the composite Fermi liquid, and it's been studied you know, tremendously over the last 20, 30, over the last 30 years nearly. So the theory of the basic theory of this composite Fermi liquid was essentially the basic physics was understood in this work by Halperin, Lee, and Read in the early 90s. And the idea behind this theory was to say that suppose you imagine that each electron captured 2 Fritz quanta to form a new fermion, which is known as the composite fermion. And this composite fermion sees reduced magnetic field, which is reduced from the physical magnetic field by an amount that's proportional to the density of electrons. And at mu equals half, its effective magnetic field is 0. And so these weird fermions, this electron plus 2 flux quanta, they do not see any net magnetic field, and they can form a Fermi surface. So based on this thinking, this physical picture, Halperin, Lee, and Read obtained an effective field theory for this, proposed an effective field theory for this metallic state, which takes the form of a Fermi surface of these composite fermions that's coupled to a dynamical U1 gauge field with a Chern-Simons term. Okay, so this theory is enormously successful, and the same framework enables one to understand various kinds of other composite Fermi liquids. For instance, electrons at filling fraction a quarter also form a metallic state, which is also believed to be a composite Fermi liquid. Bosons at filling fraction 1 could form a composite Fermi liquid. Now, it turns out that in numerics, the ground state is actually a gap version, which is induced by pairing of the composite fermions. But the metallic state is still worth studying. It's a parent state of this gap state. And in all these cases, this HLR construction of attaching flux to convert electrons to composite fermions and then coupling them to a Chern-Simons gauge field, that framework gives a description of the composite Fermi liquid ground state. Okay, so there's many successes of HLR. It explains many aspects of the observed metallic state. It predicted many other things, very surprising things that were since confirmed beautifully in experiments. But it also gives, it plays a special role in terms of unifying our understanding of the quantum Hall phase diagram. The composite Fermi liquid can be thought of as a parent state of an entire sequence of prominent quantum Hall states, the so-called Jane states, that occur near nu equals half. It's also the parent state of the non-abelian quorum Hall state of the same filling, which you can think of as being obtained by pairing composite fermions. It successfully, is backed up by numerical calculations that people have done over the decades. So it's a good theory, right? Now, despite all these huge successes, there were some theoretical questions that were vexing open questions that people thought about quite a bit in the 1990s, but ultimately abandoned without these questions reaching any resolution. Okay, so the basic physics is understood, but there are things that people wanted to understand but then gave up at some point. So let me give you two examples, the two primary examples of unsatisfactory aspects of the HLR theory. So the first unsatisfactory aspect, and perhaps the most basic one, is that there is this expectation that the theory should make sense when you restrict the electron motion to within the lowest Landau level. So you could be in a situation where the Landau level spacing h bar omega c is much bigger than the strength of the inter-electron interaction, in which case it should be sensible to throw out all these higher Landau levels and focus just on the lowest Landau level and define the problem within that lowest Landau level. Okay. Now, this business of projecting to the lowest Landau level is something that HLR is totally ill-suited for. In the mean field description of HLR, the effective mass of the composite fermion is just the bare electron mass. And the limit of projecting to the lowest Landau level corresponds to taking the bare mass to 0. So then there's a question of what happens, right? What is then the right bare effective mass of the composite fermion? Or does the theory itself change in some dramatic way? And all the leading lights in the quorum Hall field were thinking about this kind of question in the late 90s, given a selection of names here. But the dust never really settled, and people just moved on to other problems. Now, we're a long time away from the late 90s, so why return to this kind of thing? So in modern times, many of the problems that many of us are thinking about now, I personally think it would be useful to have the experience of learning to work within the lowest Landau level. So that's my motivation for revisiting this kind of question. Okay. So another unsatisfactory aspect of the HLR theory is probably more familiar to people because it's gotten some attention in recent years. For the nu equals half composite Fermi liquid or any state of the microscopic Hamiltonian at nu equals half, within the lowest Landau level, the theory has a particle hole symmetry that the HLR formulation, because it's not a lowest Landau level formulation, is blind to. And this issue was also identified in the 1990s, but a possible solution emerged only in the last 2 years, thanks to ideas initiated by Sohn, and many people in the panel have worked on it. This goes under the name of Dirac composite fermions. So all this progress that happened in the last few years on resolving this particle hole symmetry issue, essentially, sidestepped the issue of lowest Landau level projection and approached particle hole in a way that did not require you to think about projecting to the lowest Landau level. So it's very clever strategy that introduced by Sohn, which led to this progress. But since I believe that the particle hole issue is essentially resolved, I'm not going to talk about particle hole at all today. Okay. Instead, I'm just going to focus on the lowest Landau level projection. So let's talk about what the problem is, right? Let's define the problem first. And so this slide defines the basic problem, that's the basic theoretical problem in the quorum Hall effect, in the quorum Hall regime in the lowest Landau level, right? So we have particles moving the lowest Landau level with two-body repulsor interactions. So let M be some basis for single particle states in the lowest Landau level. So many body states will be spanned by states like these, M1, M2, M3 to Mn. N is the number of particles. And we should symmetrize or anti-symmetrize these states depending on whether we are talking about bosons or fermions. And the Hamiltonian has no kinetic energy. It only has interaction energy, which is written in terms of density operators that are projected to the lowest Landau level. So these density operators after projection, they satisfy a well-known algebra known as the GMP algebra, after Gervin, MacDonald, and Platzman. In the math literature, I believe this known as the W infinity algebra. So the commutator of two of these density operators at two different momenta closes. You get the density operator momentum q plus q prime, but with some prefactor which depends on q cross q prime. And this coefficient u of q is up to a form factor, just the Fourier transform of the microscopic two-body interaction. So this is the question, this is the problem posed in the lowest Landau level in the quantum Hall regime, and everything, all the physics has to follow just from this Hamiltonian, right? So there's no, the only length scale in this problem, so let's say we assume a short-range interaction, say Coulomb interaction or something. The only length scale is the magnetic length, and the only energy scale is the strength of the interaction, right? So that's the question. Now, though for electrons, composite Fermi liquids of electrons, the dust never settled, also very important in understanding composite Fermi liquids of bosons at Philip fraction 1 in the 90s. And this, the most important progress came from two papers. The first by Pasquier and Haldane in 1998. So both these papers dealt with the basic problem posed in this slide, but the method of solving it was interesting. And it's not very different conceptually from methods used, say, in quantum magnetism to solve spin Hamiltonians, something like that. So given a density operator satisfying this GMP algebra, what Pasquier and Haldane found was a representation of this density operator in the Hilbert space of the many-body boson system in terms of fermionic partons. So these partons should be thought of as the lowest Landau level version of the composite fermions. Okay? And like with any parton description, there's a highly redundant description. In fact, it's extremely highly redundant compared to a typical, the more familiar kinds of parton description in quantum magnetism. And so one needs to impose constraints to recover the physical Hilbert space. Now, it turns out that these constraint operators themselves obey the GMP algebra, but with an opposite sign. So there's a huge, the symmetry group formed by these, generated by these constraint operators is a huge group. In fact, the symmetry algebra formed by these constraint operators, because it's GMP, it's itself a W infinity algebra. So in Read's paper in 1998, he described this by saying that this parton representation has a huge gauge redundancy, which is this W infinity gauge redundancy. It sounds formidable, but fortunately, if you make a mean field theory, look at a mean field state, which describes the composite Fermi liquid, almost all of this gauge structure is broken down to U1 by the mean field. So then the low energy theory, you expect it to be that of a Fermi surface coupled to a U1 gauge field, which sort of makes sense, right? And Read treated fluctuation effects diagrammatically by summing ring and ladder diagrams within a conserving approximation, and calculated with many physical properties, and they yielded sensible final results. So that's basically where things had stood, more or less, since then. There's been almost no further development. But there are many open questions that were left behind by this progress, just that no one tried to think about these questions before. So we could ask, what is the low energy effective field theory that comes out of this Pasquier Haldane-Read approach? How is it related to the HLR theory? And can we treat, neighboring topologically ordered quantum Hall states within this framework? Can we generalize to other problems? None of those questions have been addressed in the 22-year-old literature since these papers have made an appearance. So this talk, I'm going to focus on just one question on what the low energy effective field theory is that comes about from this approach. So that's the focus. So there is a suggestion in the literature for an effective field theory that sort of this approach. And the suggestion is, can be, the Lagrangian is here, but the suggestion can be worded by saying that think about composite fermion not as an electron with flux attached, or in this case, a boson with flux attached, but rather as a fermionic vortex. So the field theory has a Fermi surface of these psi-V fermions that is coupled to a dynamical U1 gauge field, and there's no Chern-Simons term for the dynamical gauge field. Rather, it's coupled to a background gauge field, capital A, through a mutual Chern-Simons term, and this background Chern-Simons term, so this mutual Chern-Simons field. So this structure of the theory was suggested in Read's original paper, but not explicitly derived based on the actual calculations that were done in that paper. And it should be contrasted with the HLR, usual HLR theory, perhaps with renormalized parameters, which has a fermions coupled to U1 gauge field, but with a self-Chern-Simons term for the dynamical U1 gauge field, right? So these are two possible different Lagrangians that describe composite Fermi liquids of bosons. The Lagrangians are clearly distinct. So do they describe the same IR physics, or are they describing different phases of matter? So none of that is clear, right? And the question one could ask is which one of these, or if either, is actually obtained if we start with the Pasquier Haldane-Read microscopic theory of bosons at nu equals 1. Now in the subsequent years, there's two, further places where this theory made an appearance. One is by two of the panelists in this meeting. One did, was to, in one, the idea was to do a duality on the original microscopic bosons, to go to bosonic vortices and then do flux attachment to fermionized vortices, and that produced this theory, but this was not a lowest Landau level approach. And with Chong Wong, a few years back, I myself proposed that perhaps in the limit of projecting to the lowest Landau level, the standard HLR theory, there's a Fermi surface Berry phase that then converts this theory to this second theory to the first theory. But we don't know if any of these things are actually correct. So let me give you our answers straight away in this work that we've just done with Jihan Dong. So starting from this Pasquier Haldane-Read approach, we derive an effective field theory. And it turns out it's what's known as a non-commutative field theory of fermions with coupled to U1 gauge field, but without any Chern-Simons term, just like Read had suggested in his paper. The difference, or rather the thing that was not explicitly suggested, was that it's a non-commutative field theory. And then the second result is that there's an approximate mapping of this non-commutative field theory if we restrict ourselves to long wavelength, low amplitude gauge fluctuations. And that approximate mapping, if we use that, we end up with a commutative field theory, which turns out to be exactly the HLR theory, but with subleading corrections, and with parameters determined with the interactions. So this map uses results of another of our panelists, Nathy Seiberg-Witten, in 1999 in some famous work. I'll discuss that more as we move along. But these are our results. So I think we've answered this question of what the effective field theory is. And amazingly enough, it turns out to be just HLR, but with some corrections.
So can I ask a question here, Senthil? So can you go back to the previous, just so that I hear what the claim is? Can you go, no, one more?
Yeah.
Yeah, so by HLR here, you mean the lower Lagrangian?
Exactly.
Okay, and so, so there are no Berry phase effects or these Fermi surface.
Nothing, yeah.
That's not present for bosons at nu equals 1.
Not according to what we get at the end of the day.
This is against your own paper in 2016. Is that right?
Yeah.
Is that?
Indeed.
Oh, okay. Sorry.
No, Berry phase do show up, but in a way that seems to be, as far as I can tell, opposite to what we imagined. So,
thank you.
Yeah. Okay. So let me make a few remarks on non-commutative field theory. A lot of the high energy physicists listening in are totally familiar with this. lot of the condensed matter physicists are probably totally unfamiliar. So these are field theories defined in a space-time where the spatial coordinates do not commute. Now, there's a long history in the physics and math literature, and there was a phase of about 5 years when it was very much, it was extensively studied in the HTH literature, and then it was just dropped, right? Now, of course, condensed matter physicists are completely familiar with such a space. It's just the lowest Landau level. So perhaps we shouldn't be surprised that effective theories within the lowest Landau level or non-commutative field theories. Now, as part of this wave of activity for incompressible quantum Hall states, there was a proposal that the effective field theory, a proposal for an effective field theory description in terms of non-commutative Chern-Simons theory by Susskind and by Polychronokos and so on. So this, is an alternate to the standard commutative PQFT description. One could ask what value it adds over the standard description and what the connection to the microscopic, say, two-body interacting Hamiltonian is. So I'm not really sure, but there is some literature on this. Several people have worked on it subsequently, so maybe somebody knows. So here instead, I'm going to focus on the compressible metallic state of bosons at mu = 1. Okay. So let me introduce the Pasquier Haldane-Read parton construction. This is designed to describe bosons at mu = 1. At least that's the problem it's best suited for. So the physical states, let's represent them by M1 to Mn, which is which Landau orbitals are occupied, and these are symmetric. So the right-hand side expresses these physical states by starting with a Fock vacuum of fermions and then acting with n creation operators of fermions. These fermions are two indices, n and m, and we anti-symmetrize over the n index. Okay, so epsilon is the completely anti-symmetric tensor of rank n. Now, because epsilon is completely anti-symmetric and the fermion operators are anti-symmetric, automatically the right-hand side describes symmetric states in the Hilbert space. So this is a legitimate representation of the many-body boson Hilbert space. Now, since these fermions are two indices.
Senthil?
Sure.
Yeah. So what about a single boson creation operator? That's how many of these fermions product together?
So the single boson creation operator is not easily represented within this framework.
Okay.
Right. So you work with states with fixed number of particles.
Okay, I see.
Okay. So CMN, the dagger, the joint, the Hermitian conjugate of C dagger and M, or obey the usual fermion anti-commutation relations. Right. Now, physical states, since they are completely anti-symmetrized in the n index, physical states are singlets under SUN rotations to the right of this matrix CMN. So physical states are invariant under this sort of SUN rotation. So consequently, the generators, the Hermitian generators for these SUN rotations satisfy a constraint that rho right acting on a physical state just gives you the identity matrix. Now, you can also contemplate doing left rotations, SUN rotations to the left on the CMN, and those are generated by these operators, rho L, and those are physical operators, and they correspond to things that you would measure in the boson system. So there's a huge gauge redundancy, if you wish, which are these SUN right transformations. But of course, ultimately, we're interested in n going to infinity. So really, there's some SU infinity sort of redundancy. And that's what corresponds to this W infinity redundancy that I mentioned before. And we want to think about M and N as single particle basis states for a Landau level. Okay. So this looks formidable. Now, it's made slightly less formidable looking by moving to a momentum space formulation. So we Fourier transform this operator CMN using the magnetic translation operator. Take the matrix elements of the magnetic translation operator, e to the I k dot r, where r is the guiding center coordinate. take its matrix elements and use that to define the Fourier transform of CMN, that gives you a momentum space fermion operator, which is a usual fermion operator satisfying the usual fermion anti-commutation relations. Now we can use the same Fourier transform to Fourier transform the density operators, row left and row right, which are fermion bilinears. And if you take those Fourier transform fermion operators, and then you ask what their algebra is, it turns out that row left satisfies the GMP algebra, and row right also satisfies GMP, but with the opposite sign, and row left and row right commute with each other. Okay, so this is a nice algebraic structure in momentum space. And the Hamiltonian.
Sorry, can you define rho L and rho R? I missed that.
Oh, sorry. So let me go back to the previous slide. So rho L, rho R are the generators of the SUN right rotations, and rho L are the generators of the SUN left rotations.
Okay, thank you.
Okay, sure. So if you wish, this slide provides a complete formulation of the problem in terms of fermionic partons. You have the Hamiltonian, it's written in terms of these physical projected density operators. We have a representation of these density operators in terms of CK, which can be traced back from the one in the previous slide. And these operators satisfy this algebra, but then this representation comes with a constraint in the form, oh, sorry, this is a typo here. This should be rho right. Rho right of Q acting on physical states is 0 for all non-zero Q. And rho right itself satisfies this algebra, and rho right commutes with rho left. Okay, so if we could solve the system with these constraints, we are done.
Sorry, Senthil. So mathematically, what is the relation between GMP algebra and the SUN algebra?
Yeah, so when I went to the SUN algebra in the limit of n going to infinity and choosing these states to be the basis states for a Landau level just becomes the GMP algebra.
Okay.
Okay. So GMP can be roughly thought of as taking a special kind of limit of SUN when n goes to infinity. Okay. So it's a horrendously, on the face of it, it's a horrendously complicated parton description. Right? We usually work with partons with SU2 gauge structure, U1, or I know Chenke, you worked with SP4 gauge structure, but here we're doing SU infinity. Okay, or at least Pasquier Haldane-Read, we're doing it in those days. Okay, so the density operators of fermion bilinears, they have some expressions in terms of these CK fermions. So if we plug that into the Hamiltonian, we'll get a 4 fermion Hamiltonian, which of course we don't know how to solve. So let's try to solve it in Hartree-Fock. And the simple thing to do is to look for a state that preserves all the global symmetries. And a simple such state involves a translation invariant state, would involve looking for a state where this fermion bilinear C dagger K C K prime has an expectation value delta 2 of K minus K prime times some occupancy number nk. And indeed, you can find such a Hartree-Fock solution to this Hamiltonian. And within this Hartree-Fock, the fermions will acquire a dispersion and form a Fermi C with an area set by their density. So this then gives you a mean field description of a composite Fermi liquid. Now for what follows, I'm going to approximate this dispersion as parabolic. It's not a very crucial approximation because we don't really care about what happens near K equals 0. We only care about what happens near the Fermi surface. And the actual function is something much more complicated, but it'll be convenient to just take parabolic dispersion relation. So we can write down a mean field action in terms of these CK fermions. It's just the standard action for a non-relativistic fermion with a parabolic dispersion, but we should remember the fermions are at finite density. Okay. So the next thing to do as a standard in these parton things is to go beyond mean field. So Read did that. So this is a typo, it's just Read. Did that within this diagrammatic conserving approximation, but that's not our goal here. We want an effective low energy theory, right? So the standard thing to do would be to ask about, how much of the gauge symmetry is actually broken. So this huge gauge structure, this infinite gauge symmetry that's generated by rho r, and basically all of it is broken except when Q equals 0. No, rho r when Q equals 0 is just the total number of particles. So that doesn't really generate a gauge transformation. It's the global U1 symmetry of the system. So the breaking of the gauge symmetry generated by rho r is weak as for small q. This means the theory of fluctuations, the important fluctuations beyond mean field, a small wavelength gauge fluctuation generated by rho r on top of the mean field theory. So the question is, how are we going to deal with these small q gauge fluctuations on top of this mean field? Right? Now, there's a difficulty in incorporating these gauge fluctuations. In momentum space, the mean field state is simple, but the action of these rho-right transformations is extremely complicated. Rho-right mixes states at different momentum. Okay. So there's an extremely complicated action of these gauge transformations if we want to work in momentum space. So this is common in any problem with the gauge field. In real space, it's very simple to state the gauge transformation, but in momentum space, it's complicated. So you could go back to the Landau orbital basis, the MN basis, and then the gauge transformations look simple, the SUN rotations from the right, but then the mean field state is complicated. The mean field state only looks simple in momentum space. So this is the technical problem with doing any simple theory of, at least standard looking theory of gauge fluctuations on top of the mean field. So we found a way to circumvent this problem, and that's to take.
You have 10 minutes. 10 minutes.
I have 10 minutes. All right. That's good. So it turns out that there's a very convenient but somewhat abstract formulation which enables us to get around this problem. That is to define the field that, in terms of which we write the action, somewhat more abstractly, and define it as a function of this guiding center coordinate. Okay, so there's several different points of view on such a field. One point of view is to say that, look, the right-hand side is the definition of the quantity that I'm talking about. So CK is a Fock space operator. It destroys a fermion with momentum K, or it's an operator in the single particle states of the Landau level. It's a guiding center coordinate. So this object, this integral defines some object, C of R tau, where C acts in Fock space, and R is the Landau level guiding center coordinate, right? So there's a lot one could say about these kinds of fields, but so we'll just take a pragmatic point of view. We'll just use this Fourier transformation as the definition of C of R tau, and just work with these. And anytime we are confused, we'll go back to this Fourier transformation. Okay. This Fourier transformation, using this Fourier transformation definition, we can deduce many properties of such objects, such fields that are defined in non-commutative space, because the guiding center coordinates form a non-commutative space. For instance, suppose I had two scalar fields, product, and I took the product of such fields at the same spatial point, or the product of such fields is not given by the usual product, but rather it's given by what's known as the star product, which is associative but not commutative. And this structure of the star product is easily deduced from the Fourier transform definition using the known property of the magnetic translation group that's generated by the CDIK.R operators. Okay. So there's a parameter here, this theta, which is related to the commutation between the two components of the guiding center coordinate.
Senthil, the K's in the Fourier transform are standard K's that commute with each other, right?
Absolutely, yeah.
And the R's?
The R's are not the R's don't commute with each other.
So if I look at the formula above, C of R and tau, the argument R, these R's do not commute.
Yes, indeed.
The integration variable K, they do commute.
Absolutely, yeah.
Okay.
And the CK tau obey the usual fermion algebra.
Absolutely, yeah. That's right. So this non-commutativity parameter, the extent to which the guiding center coordinates don't commute, in our case, it's just the magnetic length squared up to a minus sign. So this is often called the non-commutativity parameter. Now, it turns out that it's easy to define derivatives of such fields. One can define integrals over such fields. Just take the trace over the Hilbert space band, or just take the trace over the Landau level. Okay, so how does this formulation help? So in this more abstract formulation, there's a very simple action of transformation generated by row left and row right. They just correspond to taking star products with unitary matrices, UL or U right. So for instance, U right can be written as e to the I theta r, where theta r is a function of this guiding center coordinate. And we define the exponential through its power series, with all products occurring in that power series being star products. So the gauge transformations look simple in this framework, but then the mean field action also looks simple. It's just it just takes this form where we take C bar and star it with dCr d tau, and likewise we replace this product of these two gradients with the star product. So now it becomes clear how to include gauge fluctuations. We just require the action be invariant under long wavelength right gauge transformations. And so we replace all derivatives here by covariant derivatives. Okay, so that's our answer, that we get this non-commutative action for the composite Fermi liquid. So the time derivative and spatial derivative terms become covariant derivatives. So A0, since it imposes this constraint that rho right is equal to the identity, multiplies the mean density rho bar as well. And these covariant derivatives are defined in just this manner, where it's the ordinary derivative plus, even though we only have U1 gauge fields, because these products are not commutative, we have to define whether we take the star product to the left or the star product to the right. The dynamical gauge field multiplies the C operator to the right, and the background gauge field that we use to probe the system multiplies the C operator to the left. So these correspond to the right gauge transformations, and these correspond to the left gauge transformations. And these fermions are at finite density, and they form a Fermi surface, while the gauge fields vary slowly on the scale of the magnetic length. And this theory one can explicitly check, and by construction, it has a gauge invariance, which is a bit more complicated than the standard commutative gauge invariance. But for this U1 gauge theory, because it's in non-commutative space-time, the gauge transformation sort of looks more like what we are used to with non-abelian gauge fields. Okay, so the theory has a Fermi surface plus a dynamical U1 gauge field without any Chern-Simons term, but the price to pay is that it's formulated in this non-commutative space-time. Okay, now Hartree-Fock theory gives an estimate of the bare effective mass and star in terms of the interaction strength. One can derive an explicit answer with numerical factors and so on. So there is an effective field theory that we sought for this composite Fermi liquid. So how do we compare this with previous proposals? So all the previous proposals, the HLR or the fermionic vortex liquid, they're all ordinary commutative field theories. Okay. While here, what I've written down for you is a non-commutative field theory. But the non-commutativity occurs on the scale of the magnetic length, and we can hope to approximate long wavelength gauge fluctuations in terms of a coarse-grained commutative field theory. Okay, so that's what we want to do. Now, there's a key tool that helps us to do this, and this was discovered by Seiberg-Witten in 1999, and they mapped pure non-commutative gauge theory with gauge fields A mu to a commutative gauge theory with Hartree gauge fields A hat mu in a systematic expansion in powers of this non-commutativity parameter theta. So this expansion is local in that the coefficients of this expansion only involve fields and derivatives at the same space-time point. It only maps gauge equivalent configurations to each other. This very clearly explained in that paper, and Nati, of course, is in the audience, that there's no mapping of the gauge groups directly. It's only mapping of gauge equivalence classes. And in particular, the gauge transformation parameters are mapped as functions of the gauge field configurations themselves. So here we'll need a small generalization of this that includes the fermion fields. Now I should say that subsequent to the work by Seiberg-Witten, there's been thousands of papers on this since. But there's two developments that I should mention. For pure U1 gauge theory, there's an exact non-perturbative Seiberg-Witten map due to many people. Hong Liu, one of my colleagues, was someone who worked on it. And there's a very appealing physical interpretation of this result in terms of a familiar mapping that between the Lagrangian and Eulerian descriptions of a fluid by another colleague of mine, Roman Jakiv and Soyang Pi and Polykranakos, and related ideas by Susskind in those old days. But in any case, this is something that's extremely well explored in the field theory community for mapping between the non-commutative gauge theories and commutative gauge theories, at least in as an expansion in powers of theta. So here, what we did was just to do this map in the problem that we are interested in to linear order in theta. So we expand all non-commutative gauge fields and gauge transformation parameters to linear order, write them as commutative gauge fields and gauge transformation parameters, plus a correction that's of order theta. And this map to this order of theta can be found very explicitly by requiring that the hatted fields satisfy ordinary U1 gauge invariance, not this weird non-commutative gauge invariance, for both the dynamical and the background gauge fields. So we could work that out, and we found this map. And then the strategy is, once we know this map, to plug it into the non-commutative gauge theory action and see what commutative gauge theory we get. So it's a coarse-grained version of that theory where the gauge fluctuations are treated at length scales much bigger than the magnetic length. So the algebra is pretty complicated. It's straightforward, but it's complicated. But at the end of the day, this is what we end up with. The effective commutative Lagrangian, I've written it as sum of two terms. The first has the structure, has a very familiar structure. It's a Fermi surface coupled to a U1 gauge field with Chern-Simons term for the dynamical U1 gauge field. Okay, and the second term involves, for instance, coupling between the dynamical electric field and gradients of the density, or correction terms to terms that are already present in the first Lagrangian, terms that are of order the internal magnetic field times this theta parameter. Now you'll recognize the first term is just
can you step back? The original theory, before you perform the map, did it or did it not include the Chern-Simons term?
No.
So where did the Chern-Simons term come from?
It came from your mapping, but I can say something more physical about it maybe in one slide.
Okay. Here, capital A is at zero magnetic field, net zero magnetic field for capital A.
Yeah, so capital A is just the excess field, the probe vector potential. That's right, indeed. Okay. So the first term is just the standard HLR theory with the right effective mass determined by interactions. And the second term is small. So the correction is the leading order correction that we've calculated as it's small so long as we restrict the long wavelength, low amplitude gauge fluctuations, which is what we want to do in any case. So good. So so the commutative theory has a Chern-Simons term, which is absent in the non-commutative theory, which is exactly the question that Nathi was asking. So this is related to the non-trivial form factors in the density operator in the non-commutative theory. So I did not show this formula, but if you express the, say, the row left operator, or the row right operator in terms of the density operators, there's a, it's a fermion bilinear with momentum transfer Q. The density operator momentum Q is a fermion bilinear with momentum transfer Q, but with a form factor, which is non-trivial. It's of the form e to the I over 2 k over k cross q with a plus or minus sign, depending on whether we are talking about the right or left densities. So roughly speaking, these form factors correspond to a non-trivial Berry phase in the system. And this then gives rise to an anomalous current. And somehow this Seiberg-Witten mapping knows about this anomalous current. And when you map it to the commutative theory, you lose this form factor, but instead it captures the effect of the form factor by having an anomalous current. And that seems to be why you get the Chern-Simons term. And Subir, since you asked a while back about the effect of Berry phase, this is how the Berry phase seems to play a role. It's there, but what it does is to take the non-commutative theory without a Chern-Simons term and give you in the commutative limit a theory with a Chern-Simons term. Okay. This is the rough understanding for how the physics of why it works out the way it did. Now, once we've obtained this effective
I'm still puzzled. If you can go back. So for theta equals 0, everything should be the same, right? Commutative, non-commutative, it's just a special case.
Oh, very good. No. So there is a subtlety here, which I should be, good. So theta equals 0. So remember the theory is at finite density. Okay. So the density of fermions is 1 over 2 pi LB squared in this problem. That's 1 fermion per magnetic length. So the finite density, so density can be written as 1 over the non-commutativity parameter, theta. So in the theta going to 0 limit, there is a term, the Chern-Simons term comes from a term that is order of the mean density times non-commutativity parameter, right? So even though formally this term is of order theta, it has a non-trivial limit when theta goes to 0 because we are working at a density that's of order 1 over theta. Is that good, Bharti?
Well, I take your word that this is how it comes. I don't see the details of how it comes.
Yes, I did not write the explicit formulas, but mathematically, where it comes from is to take this term in this action, I A0 rho bar, and if you replace A0 by its expression in terms of the hatted fields, A0 hat plus the correction, then the correction is of order capital theta times rho bar, right? Now rho bar is proportional to 1 over theta. So even though that correction term is formally of order theta, since it multiplies rho bar, it manages to give you an order 1 Chern-Simons term.
Senthil, we are, I think we're a little over time. Do you want to conclude? And
that
take
was
away.
Almost my last slide. So maybe I'll say one thing and then I'll go to my last slide. So one thing we can do once we have this commutative effective theory is that we can study, Jane states, we can perturb it and do other things which are technically harder to do within so there's always use of effective theory within the microscopic, completely microscopic approach. So let me just conclude. There's many other things that we want to do. We want to, generalize for other composite Fermi liquids. Some generalizations are easy. Some not so straightforward. For instance, the most important generalization perhaps is to fermions at half filling. We don't know how to do that yet. And in all cases, I think it's completely natural that a lowest Landau level theory is non-commutative. Now, there's other generalizations that are possible. For instance, these methods can be used to produce useful mean field theories of multi-component quantum Hall-like systems, total integer filling, which show up in many different contexts. So in any case, let me just stop here. Thank you.
Okay, thanks a lot, Senthil. We're over time, but we have several questions as well. Many of the questions I think are more sort of clarificatory questions, which maybe you can answer directly on the Q&A, but maybe I'll pick a couple of them that are a little, maybe a bit more provocative. So one of the questions from Liu Jun Zhou was, How come intuitively, how do you understand SUN n going to infinity gauge group ending up as a U1 gauge group at the very end?
Yeah, you know, it's U1 only in some formal sense, right? It's there's really a huge group of transformations that there is a U1 in the commutative field theory, which is just the standard U1. But that's what I explained right at the beginning. It's because most of that big gauge group is broken down by the mean field ansatz. Right? It's explicitly broken at the mean field level. So the only thing that survives is the U1 subgroup of SUN.
Okay, let me ask you two other quick questions. One is from Ruben Verison. In your non-commutative setup, space and time still commute. Can you imagine a scenario where time and space do not commute, which you could already be
punt that to
explored?
Nathi, I think. It's not relevant in the quantum Hall context, but perhaps relevant in some quantum gravity context. So Nathi or Shamit wants to answer that. John McGreevy.
Okay.
Andreas.
Okay, maybe I'll ask you the very last question, unless someone has a comment right now. Does Nathi have a comment? Or?
Nathi, the question was about theories where space and time don't commute.
Oh, I don't know anything about that. To the extent that space and time don't commute, it's only for theories where time is Euclidean. I don't think it makes sense for Lorentzian time not to commute.
Okay.
Euclidean space-time, well, this is another special coordinate, but with Lorentzian time, time commutes. Otherwise, I don't know what we're doing, right? We want time evolution, you know. Like saying that, you know, the talk will end at some point. That should be a number. It shouldn't be something that doesn't commute.
Well, maybe this talk, it's not quite true, but we are going a little over time. But let me ask one last question. So the question from Chong Wang, does this mean that if we want to study something like 2kF scattering, I need to honestly work with the non-commutative theory since momentum is no longer small?
Yeah, I believe that's the safe thing to do.
Okay, so maybe we'll move on to the next speaker. We had budgeted for a break, but we've gone over the break time. So let's just thank Senthil. And Senthil, if you can stop your screen share, we can move to the last.